Hey you guys, this is Mr. Millings, and in this video we are going to do an advanced combined gas law problem. So grab your scientific calculators and let's jump right in with an example problem. In this example problem it says, initially nitrogen gas is pumped into a flexible spherical container that has a radius of 120 centimeters, a pressure of 1,649 millimeters of mercury, and a temperature of 176 degrees Celsius. If the radius of the container changes to 92.7 centimeters at a pressure of 21.5 psi, then determine the temperature of the gas in degrees Celsius, and we need to assume a constant number of moles here. So if we take a look at this problem, there's a lot going on. It says that initially we have a spherical container, so I'm going to draw our spherical container right here. And what we know about this spherical container is that we're going to pump some nitrogen gas into here. So we're going to pump some N2 gas into this spherical container. And it says that the spherical container is flexible, meaning it can expand or it can contract. But what it does tell us is that the radius of this spherical container initially is 120 centimeters. So we know that the radius of this spherical container is 120 centimeters, and we also know the initial pressure of the gas that is in here. So we have some nitrogen gas that's in here, and initially we know that the spherical container has a radius of 120 centimeters, and we know that the initial pressure, or P1, is equal to 1,649 millimeters of mercury. We also know that the temperature of the nitrogen gas that is in here initially is 176 degrees Celsius. And so if we read on, what it says is that the radius of the container is changing to just 92 centimeters. So if we take a look, the radius of our spherical container here is getting smaller. The radius is changing to just 92.7 centimeters. 92.7, sorry, let me erase this. 92.7 centimeters. And so inside of here we still have our nitrogen gas that's in here. And if we read on, what this also tells us is that the pressure is changing to 21.5 psi. I apologize. 21.5 psi is what the pressure of the gas is changing to. And so what we have to figure out is, given the set of conditions here and the changing set of conditions, we need to figure out what the temperature, or T2, of this gas is going to be in degrees Celsius. So now that we kind of understand what's happening here, we can see that this is going to be a combined gas law problem. We know the initial pressure of the nitrogen gas. We know the initial temperature of our nitrogen gas. So how can we get the volume of the nitrogen gas? Or how can we get V1? That's not given in the word problem, but we do know that this is a spherical container and we know the radius. So the initial volume here is going to be the volume of a sphere, which is 4/3 pi r cubed, right? And same thing down here. We can figure out the final volume of this spherical container that this gas is in, keeping in mind that gases take the shape and volume of their container by using the formula of a sphere, or the volume of a sphere here, to figure out the volume, right? The volume of a sphere is 4/3 pi r cubed. So even though the volume is not given to us directly, we can calculate the volume. So let's go ahead and take a look at what's happening here. We can see that this pressure here is in millimeters of mercury. This pressure is in psi. We can also see that the temperature is in degrees Celsius, and before we can do any gas law problems, we always must convert the temperature to Kelvin. So let's go ahead and set up some variables here. We can see that P1 is 1649 millimeters of mercury. We can see that P2 is 21.5 psi. We can also take a look and see that the temperature initially is 176 degrees Celsius, and the final temperature is what we're trying to figure out in degrees Celsius. That's what we're asked to figure out. So let's figure out the volume. Let's figure out our initial volume. To get our initial volume here, we're going to have to take 4/3 pi r cubed. So if we take 4/3 times pi times our radius, which it tells us the radius here initially is 120 centimeters, and we're going to cube this. So if we put this in our calculator, if we take 4/3 times pi times the radius, which is 120, and we cube that, we are going to end up with 7.24 times 10 to the 6th. 7.24 times 10 to the 6th centimeters cubed, which is equal to 7.24 times 10 to the 6th milliliters. Keep in mind that these two units are used interchangeably. 1 milliliter is the same thing as 1 cubic centimeter. So we know the initial volume here. It's 7.24 times 10 to the 6th milliliters. Let's figure out the final volume. V2 is going to equal 4/3 pi r cubed. So we'll take 4/3 times pi times our radius, which is now 92.7 centimeters. And we're going to cube that. So when we put this in our calculator, when we take 4/3 times pi times the radius, which is 92.7, and we cube this, we are going to end up with 3.34 times 10 to the 6th. 3.34 times 10 to the 6th centimeters cubed, which is the same thing as 3.34 times 10 to the 6th milliliters. So now that we have the volume units the same, we have milliliters here and milliliters here, we now have to take a look at our other variables. We can see that the temperature initially is 176, so we have to add 273 to get this to Kelvin. So we have 176 plus 273, and that's going to equal 449 K. And then what we have to do is we have to convert this to either PSI or millimeters of mercury. So let's go ahead and use millimeters of mercury. Let's go ahead and convert this second pressure to millimeters of mercury. So we know that there are 14.69 PSI and 760 millimeters of mercury. And when we put this in our calculator, 21.5 times 760 divided by 14.69, we're going to end up with 1,112. 1,112 millimeters of mercury. So we have millimeters of mercury here and here. And so what we're asked now to do is figure out the Celsius temperature. So let's go ahead and figure this out here. If we take a look, let's see if we can make some room here. We know that P1 V1 over T1 equals P2 V2 over T2 if we're using the combined gas law to solve this problem. And so in this problem, we're asked to solve for T2. So if you manipulate this formula here, you're going to end up with T2 equaling P2 V2 T1 all over P1 V1. So if we take P2, which is 1,000, let's go ahead and make some room here. This is going to equal P2, which is 1,112 millimeters of mercury, times V2, our second volume here is 3.34 times 10 to the 6th milliliters, times T1, which we figured out was right here, 449 K, And we're going to end up dividing this by P1 and V1. So P1 is 1649. And V1, if we take a look here, is 7.24 times 10 to the 6th milliliters. And so when we put this in our calculator, we'll take 1,112 times 3.34 times 10 to the 6th times 449 divided by 1649 divided by 7.24 times 10 to the 6th. And we are going to end up with 139, or 140, I apologize, 140. Let's see what unit is left over. This cancels with this. This unit cancels with this, leaving us with Kelvin. So this is not our final answer. Keep in mind this is T2, but this is not our final answer. The question wanted the final temperature in degrees Celsius. So to get our degrees Celsius, right, to get our degrees Celsius now, what we have to do is we have to take our Kelvin temperature, which is 140, and we subtract 273 to get our Celsius temperature. And so when we take 140 minus 273, we're going to end up with negative 133 degrees Celsius. And this right here is going to be our final answer to this problem. So let's take a look. If we have a flexible spherical container that has a radius of 120 centimeters and we pump some nitrogen gas in here at this initial temperature and at this initial pressure, and the pressure of the gas that is in the spherical container changes to 21.5 psi, well, then what is the final temperature in degrees Celsius of the gas particles that are in here? Well, those are going to have a temperature of negative 133 degrees Celsius. So that's going to be an advanced combined gas law calculation. If you like what you see, go ahead and click that little bomb in the bottom right hand corner. That's going to subscribe you to my channel, and feel free to leave any comments or questions in the comment section down below. And I really hope you guys found this helpful.